On the exam, I had material from 3.1, and we skipped 2.6, and I did that intentionally because historically, my experience is that logarithmic functions cause major problems with students. And it's because of the notation. Normally it's something that they're not used to seeing, so students are like, what the heck's going on here? All right? So I didn't put that on this test because I thought that that would make the test a little harder. But we've got to go back and talk about it. So logarithmic functions. I'm going to try and make this as easy as possible to understand. If it makes sense, then it makes sense. This is going to be like kind of a light bulb type thing. It's like you get it, you see it, or you don't. And until you see it, it's going to be like, what? So you need to help me try and help you see it. All right, let's recall that if I have y equals b to the x, this was called an exponential equation. Bless you. Or if you'd like, function. Bless you. That's enough though, okay? All right, so y is equal to b raised to the x is an exponential equation. See, there's an equation, right? And if we replace y with f of x, then this is a function. I asked you to graph one of these on the test. I asked you to graph 1/2 to the x. So we already know that exponential functions, what they look like, they either go like that, exponential growth, or we have exponential decay. But what we want to look at right now is the actual equation here, all right? And from this, I'm going to ask you a couple of questions, all right? So let's say I put this down as an example. What if I say 9 is equal to 3 to the x? Can you look at that and tell me, does it look like this form right here? Does it look like this? Yes? Y is 9, b is 3, x is x, right? Now can you tell me what x is that makes that equation true? 2. And you can do that just by looking, right? 3 squared is 9. We're done. So by looking at this, we know that x is equal to 2. Okay, fine. Let's do another one. What about 100? This is like, no, let's do something else. Let's do 27. 27 equals 3 to the x. So does this look like an exponential equation? Yes? Okay. I'm asking you right now, what x value do I need to put here to make this true, right? 3. 3 times 3 times 3 would be 27. Now, listen to the way I'm saying this. 3 raised to what power is 27, right? That's what I'm asking? 3 raised to what power is 27? This one was 3 raised to what power is 9? Yeah? Okay. So x is 3 here. Let me do another one. How about 8 equals 2 raised to the x? So here I'm asking, again, listen to the language here, 2 raised to what power is 8? So 2 raised to what power is 8? 3, right? 2 times 2 times 2 would give you 8. All right. So what is, if I'm using the language that I was just using here, what is this equation actually saying? 3 raised to what power is 27, right? 2 raised to what power is 8? B raised to what power is y, right? B raised to what power equals y? I'm actually going to write this down. B raised to what power equals y, right? That's the question that this equation is really asking you this question, isn't it? Now, In mathematics, we have another way of writing down this same statement. All right? Another way of writing this using mathematical notation. And here's how we write it. This statement right here is equivalent to this statement. Log. Okay? Logarithm, just when you see log, just realize that log is making you think of this question right here. All right? Log, then what I put here is b. It's like a subscript. Subscript b, x, y equals x. Okay. All right, that already looks crazy, right? I mean, you look at that, you're like, what the hell is that, right? Yes? Okay, what I'm telling you is that this is telling you to ask yourself this question. B raised to what power is y? That answer is x. All right? Let me do this same thing with the examples I just had on the board. What was that first one I had? It was 9. Okay, so if we do 9 equals 3 to the x, what would the equivalent way of writing that be using the log? You always write log. What would this subscript be? 3, and then 9, and then equals x. Okay? So when you see this, what you're saying to yourself is 3 raised to what power is 9? Right? 3 raised to what power is 9? 2. Got it? So logarithms are another way of writing exponential equations. It's a different way of writing it. All right? That's all it is, a different form. Okay, let me do this, what was it, 27 equals 3 to the x. How would I write that in this form right here? Log, so we say base 3, I'll write this down later, like how you say this, log base 3, and then what? 27, and then x. Okay, all right? So this logarithm idea is just a different way of writing something we already have been writing. All right? That's all it is. So we have this equation here and this equation here are what we call the exponential form of the equation. And then the other two, let me see, am I on camera? I'm kind of off camera here. Let me move this. Sorry. Yeah. The other two right here are called the logarithmic form. All right? So if somebody gives you an exponential equation, you should be able to convert it to its logarithmic form, and vice versa. If someone gives you a logarithmic equation, notice this is still an equation, right? Then you should be able to write it back in its exponential form, back and forth. So let's practice doing that. Let's try writing some things converting, all right, from one form to the other. And I told you I would tell you how we write that. So in words, log, when you see this, is log base b of y equals x. That's the way you read that if you were saying that to someone, if you were reading it, saying it out loud. You would say log base b of y equals x. Log base b of y equals x. What it means, though, what this really means is b raised to what power, right? B raised to the y must equal x. So now some examples, let's convert. So for this example, I want to convert to log form. All right, let's do part A. How about 5 to the third equals 125? Convert that to logarithmic form. Log, you said it, log base 5 of 125 equals 3. This is the exponential form of that equation. This is the logarithmic form of that equation. All right? This one says, of course, 5 cubed is 125. But this is also saying that 5 raised to the third power is going to be 125. Right? They're saying the same things, two different forms. Let's do another one, part B. How about b raised to the 3 equals 8? How would I write that in log form? Log base b, 8 equals 3. So this is saying b to what power, right? B to what power gives you 8? All right, let's do this one. How about 5 to the x equals m? Log base 5. M equals x. Right? So notice that in every single one of these examples, whatever the base of the exponential function is the base of the log. So if the base here is b, that's the base in the log. If the base here is 5, that's the base of the log, right? So that always carries through, no matter what example you're doing. All right, let's do the other way. Let's convert to exponential form. So this time I'm going to give you a logarithm, and you're going to convert it to the exponential form. Log base 2, 16 equals 4. So what is the exponential form of this logarithm? 2 to the 4th equals 16. Now, how did you get that? I mean, are you just kind of looking back at how are you kind of like reversing the process in your head?
Yes.
Okay, that's fine. If you do that, that's great. But I have a way that's a little bit kind of, you don't have to think about it too much, and it's quick and it's easy. The book I've never seen a book approach it this way, but I call it the loop, all right? It's a way to remember this. You create this little loop right here. Do you see this little loop? It goes like that. So what you do when you see a logarithm and you want to go to exponential form, you take 2 and you raise it to the 4 and you set it equal to 16. So it's 2 raised to the 4 equals 16. It's just a quick, easy way to get from logarithmic form to exponential form without having to actually like undo it in your head. Do y'all see it? Okay. I'll probably use that a lot when I'm doing logarithms. I'll just use this little loop idea. So let's do another one. Let's sell it, yeah. How about log base x of 5 equals 1/2? So I'm going to raise x to the 1/2 power and say that's equal to 5. That's your exponential form. All right. I'll do one more. Log base 3 of 1/9 equals -2. 3 to the -2. equals 1/9. So in both of these problems, I was doing the loop. X raised to that is 5. Here, 3 raised to -2 is 1/9. Okay, this all right? Now, let me try and show you why we want to do this, all right? Let me try and motivate this idea a little bit. Because we're going to go jump back into chapter 3 after we're done with this section. Recall that we had this formula A equals P e to the RT. We also had that other one that was a little more complicated, right? It's parentheses, and we use that on the test for number 9. Now, all the problems I gave you, I said, hey, we're going to put this much money in the bank, we're going to have it an interest rate, and I gave you the interest rate, and I told you how long we were going to leave it in there, right? And then we figured out how much money we would have at the end. What if instead I ask this question? You would like to have $5,000 in the bank in 4 years. The interest rate is 3%. How much do you need to put into the bank now? Right? Or I could ask, let's say you have, well, let's do this one. Let's say you have, let's say you have $3,000, right? And you want to turn it into $5,000, right? You're going to put it in the bank. It's going to take time for that to happen, right? So if I do that, then let's say the rate here is 3%. Then what pieces of this equation do I have? What pieces do I have? I have A, that's the amount that I want at the end, right? I have P, which is the amount that I'm going to put in the beginning. And I have R, right? The interest rate. The time I don't know, right? So what you'd be asking yourself is, hey, I've got $3,000 now. I'm going to put it in the bank at 3%. I want to know how long it's going to take to turn that into $5,000, right? What you'd have to do then, let me write the equation down. This equation would turn into 5,000. That's A, right? Equals P, which is 3,000. E to the 0.03, and then T I don't know, do I? I don't know. What type of equation is this? It's an exponential equation. And if you were trying to solve for T, right now there's no algebraic thing that you have ever been taught, unless you know what logarithms are already. There's no algebraic technique to solve for T here. Like you can't divide both sides by something or multiply. There's nothing you can do. You must convert this into its logarithmic form first before you can begin doing the problem. But I can't show you that until we work with logs a little bit. And that's why we're going back to 2.6. We want to be able to solve for time, but it's up here instead of down on the bottom. Does that make sense? Like linear equations, all the variables were on the bottom. Quadratic equations, the variables were on the bottom. This is the first time we're seeing a variable up in an exponent. So it's a little harder. That's where we're headed. Let's get back to this here. This time, this example, I want us to actually solve, all right? I'm not asking you to put this into logarithmic form or convert back and forth. We're done with that. This time I want to solve this. So part A, just to get your brains working again, 4 raised to what power was 16? 2, right? The answer was 2 here. Just by looking, right? Okay, let's do another one. How about 4 raised to what power is 1/16? -2. Now how are you getting that? Yeah, because if you put -2 here, that's the same as 1/4 squared, because properties of exponents. Let's just check it. The answer here is -2, but let's see why. 4 raised to the -2 is 1/4 squared, which is 1/16, right? So it works. I'm just checking the work here. All right, let me do another one. How about log base 10, sorry, not log base 10, part C. got ahead of myself there. 10 to what power is equal to 1 over 1,000? -3. Let's see why. What's 10 to the -3? Well, that's 1 over 10 to the third, right? And that's 1 over, well, 10 times 10 is 100, times 10 again is 1,000. So this would be 1 over 1,000. Do y'all see that? Yeah, no, yeah, okay. So that one's a little harder. Okay, how about this one? How about 5 raised to the x is 10? Yeah, this one's a little harder, isn't it? Okay, so think about it this way. What's 5 to the 1? 5. What's 5 to the 2? 25, right? 5 squared is 25. So if I do 5 to the first power, I'm getting 5. If I do 5 squared, I'm getting 25. Our answer should be somewhere in between there. My exponent needs to be between 1 and 2 somewhere, but where? We can't get this, all right? We are not going to be able to look at this and get an answer. We can do it here because if we think about it long enough and if the problem is written properly, there might be a nice number we can come up with that works. But if it's this, there's no way we can do it. Now we can't do it yet. We will be able to do it. We'll do it next class. But this is an open question right now. There's some things, some exponential equations that we just can't solve. Understand? Yes? Okay. Let's continue. I want to continue solving some equations. How about this equation? Or how about solving this? What is this equal to? Solve for x. Tell me what x is. 2. Why is it 2? Yeah, because this is asking you 2 to what power is 4, right? 2 squared is 4. How about this one? Log base 232. What's the question that's asking? 2 raised to what power equals 32, right? That's what this is saying to you? 2 raised to what power is 32? So do you know what it is? It should be 5, 2 to the 5th power. I mean, you would have to actually maybe try it. 2 times 2 times 2 times 2 times 2. These 2 are 4. Put that together with this 2, that's 8. Put that together with this 2, that's 16. Then put together with that 2, that's 32. So you get 2 to the 5th power. So the answer to this would be 5. 2 to the 5th power is 32. All right. Continue to solve. I want to know what x is. Any ideas on how we can find what x is here? What's that? Say it again. 5 raised to the negative 3. How are you doing that? Okay, so do you remember I said that little loop thing? Okay, look at what does the little loop tell us? The little loop is saying to us 5 what? Raised to the negative 3 equals x. Do you see that? If I rewrite this logarithmic equation in its exponential form, then x is sitting here ready for me to figure out, right? I just have to figure out what 5 to the negative 3 is. And that's the same as 1 over 5 cubed, and that's 1 over 125. 5 times 5 times 5 is 125. So x is 1 over 125. See, look at the position here. Look at the position of x here. X was on this side, right? So we just had to say to ourselves, all right, 2 to what power is 4? And you said 2 squared. Here, I just gave you log base 2 of 32. I didn't put anything there. I didn't put an x. But you ask yourself the same question. 2 to what power is 32? So you come up with 5. Here, I'm saying 5 to what power is x? But then I'm giving you this. I'm saying that the answer is 3. So this is really telling you 5 to the negative 3 is x. So you use the loop to create the new equation. I know it gets confusing because there's like different scenarios. But this is the nature of the beast, all right? All right. We'll do one more. H. How about log base b of 81 equals 2? I want you to solve for the only variable that's there. What's the variable there? B, right? So solve for the base. How can you do that? Square what? Square what?
Square root of 81.
Okay, so how are you doing that? Turn it into the exponential form. So I'm going to go use that loop like this. And that becomes b squared is 81, right? So solve for b, take square root of 81. I heard that, whoever said that. I did hear that. I just wanted to get to it. So what is the square root of 81? 9. Now, we're supposed to have plus or minus when we take a square root, right? Yes? Plus or minus, maybe. Let's think about this for a second, though. All right? Let's think about this for a second. Let's see what would happen if it's 9, then I would rewrite this equation like this, right? If it was 9, and this would be saying, this right here would be saying 9 to what power is 81? Well, 9 squared, right? That's true. This one right here, if I use the negative 9, like this, would be saying, what? Negative 9 to the 2 is 81, right? That's what? Well, is negative 9 squared 81? It is, isn't it? Okay, but we have a slight problem here. It's only a slight problem because of exponential functions. Remember, the logarithm is coming from the exponential function, isn't it? The idea of the logarithm came from the idea of the exponential. Do you remember our restrictions on exponential functions? When we had an exponential, they looked like this. F of x equals b to the x. Do you remember what I told you about b? It could not be 1, and it had to be greater than 0. Do you remember those conditions for exponential functions? Okay. B must be greater than 0. That will carry over into logarithms. So when you get an answer with a logarithm, the base of a logarithm cannot be negative. So even though we got positive and negative 9 here, we would scrap the negative 9 because all logarithms, the base has to be bigger than 0. So I'll put that up here, just so you know. So when you look at these two equations that we had in the beginning, when I started the whole class, I put y equals b to the x. We have the condition that b must be greater than 0 and b couldn't be 1, right? That's the assumed condition for an exponential function. If we convert this into log base b of y equals x, we have the same conditions on both of these. B must be greater than 0 and b can't be 1. So when we got -9 here, do you see that that would have given us a negative base? That's not allowed with logarithms. No negative bases. All right, so I hope that you're kind of with me still. We're going to start talking about properties of logarithms, and this is where it starts to get a little rough. All right? All right, properties of logarithms. I'm just going to put logs instead of logarithms. All right, these properties we will be using extensively. All right, here's the first property. And the first property is actually kind of nice, because we can actually rationalize in our minds that this is true. Do you agree that that's true? Why? What is this really saying? This is really saying b to the 0 is 1, right? And we already know that any number to the 0 is 1. So that was using the little loop to create this, right? To create the exponential form. So do you all agree that that's true? B to the 0 is always 1. So let me give you a couple of examples of this property. What's log base 4 of 1? 0. What's log base 7 of 1? 0. What's log base 10 of 1? 0. In other words, if you have any log, it doesn't matter what the base is. If this number is a 1, the answer is always 0. All right? Any log, any base, if you plug in 1 here, you get 0 as an answer. 4 to the 0 is 1. 7 to the 0 is 1. 10 to the 0 is 1. With me? Okay. That's our first property. Regardless of the base, if you plug 1 into the logarithm, it spits out 0. I have calculus students that still don't remember that. All right. How about the next property? Property 2. Log base b of b equals, maybe you can predict for me what that's got to be. 1. Good. It has to be 1. Now, why does it have to be 1? Because you're saying b raised to what power is b? Well, b to the first power, right? So this converted to exponential says b to the 1 is b, right? That's what that says. So some examples of this. What is log base 4 of 4? 1. What is log base 7 of 7? 1. Okay, what is log base 10 of 10? 1. So if the base is equivalent to the number inside, then your answer is always 1. That's our second property. Third property. And I think you can predict this one also. Well, this one's a little bit tougher, but I think you can get it. Third property. Log base b of b raised to the x must be what is that? X. The answer is x. Let's check it. B raised to the x must be equal to b raised to the x. Right? Do you see the loop work there? Yes? It's obvious now that, yeah? Okay. So let me give you a couple of examples of this. Log base 4 of 4 cubed is what? 3. Log base 7 of 7 to the second power is 2. Right? So if the base and this number are the same, whatever the power is here, the power gets spit out. Do y'all see that this property over here is actually the same thing? Because what's the power on this 4 right here? 1. What's the power on this 7? 1. What's the power on that 10? 1. So it's just spitting out the power, isn't it? That's what that property is saying. All right, property 4. Actually, this property, I just want to say something about it. I can't not. Do you recognize this by itself, b to the x, as being an exponential function? Yes? All right, so what we're doing here, think about it this way. If all you were looking at is this in blue, you would say, I'm going to plug in x and get an answer, right? That's an exponential function. Then what I do is I take that answer and I plug it into the logarithmic function that has the same base. And at the end of the day, what does all of this together do? It spits out x. That is because the logarithmic function and the exponential function are what we call inverses of one another. You can look at it this way. When we talked about functions, if I had a function that took the number 1 over to the number 4, that would be the function f. Let's just say, takes 1 over to 4. The function that takes it back, takes 4 back to 1, we call the inverse function. We denote it with a little -1 up there. So think about, if 1 goes into f, that spits out 4. If you take that answer and plug it into the inverse, it takes it back to 1. That's what inverse functions do. They take everything back to where they came from. So what's happening here is you're taking x, putting it into an exponential function, then into a logarithmic function, and it takes x right back to where it came from. That means that the logarithmic function and the exponential function are inverses of one another. This is in the book. I was actually supposed to start this section talking about inverses, but I figured it would be, we'll try and go a different way. So this property is actually showing that the two functions are inverses. And property 4 is the same thing but written backwards. So let me show you property 4. If you take b and you raise it to the log base b of x, the answer will be x. Now this one is harder to see. Okay, this is a harder property to see, but it's true. Question? All right. All right, 5th one. We won't use this one that much, okay? This one's used a little more, but this one, but it's a property, so I need to put it up there. All right, 5. This one is different, which is why students have trouble with it. What if you have a log, base b, and you have two things inside being multiplied together? All right? This is equal to log base b of m plus log base b of n. All right. Property 5 says, and try and listen to my words here, if you have a single logarithm with a product inside, multiplication, that this turns into what? The sum of two logarithms. Do you see that? This is a property of logs. A single log with a product turns into two logs being added. And it works the other way around too. If you have two logs being added together, you can smash them into a single log, and put the two arguments, the m and the n, that's what we call those, the arguments, we put those into a single logarithm. So if we move from this direction to this direction, it's called expanding. And if we move this direction back this way, it's called condensing. So if you expand a logarithm, you're doing this. If you're condensing logarithms, you're going back the other way. All right, let me give you a couple of examples of this. Example, expand this. Log base 4 of 4x. Use property 5. Does anyone have a suggestion here? Like, how could I rewrite it using this? What would it look like? Log base 4 of what? Okay, then what? Okay, good. Now, is that as clean as I can get it? Are you looking it up? Are you looking up the answer for us? No, okay. I thought you were calculating it, no? What about this? Log base 4 of 4. What? Have you given up now or what? Are you? No? Okay. What is log base 4 of 4? 1. Why? What property? Second property. Second property. This is 1. Okay? Do you see that? Okay. So this is 1 plus log base 4 of x. Now, this, can't do anything with this because I don't know what x is. So this is just, I'm done. So log base 4 of 4x splits into 2 and then becomes this. Let's do another one. Another example. I'm not ready for the next property yet. I'll leave the property up there. I want us to expand log base 5 of 1/25 x. Yeah, that'll work. Let's go xy. I'll see if I can push you a little bit further. So what now? What do you mean by 3 steps? You're right, but I want to make sure. 3 logs, good. You're going to have 3 logarithms because you have multiplication, multiplication. If you have 3 things being multiplied, you're going to have 3 logarithms. Now the property says that if you have 2, you can split it up into 2, but you can extend this. Imagine if this n had another multiplication in here, right, times p. Then this would become n times p, and then that one would split into 2. So if you have 2 multiplications becomes 2, 3, 3, 4, 4, 5, 5, right? It doesn't matter how many there are. So what would this be? Log base 5 of 1/25, good. And then plus log base 5 x plus log base 5 y. Good, that's it right there. Are we done? These 2 I can't touch because I don't know what x is and I don't know what y is. But this has just numbers in it, right? You see how there's just numbers here? Do you recognize 1/25 as a power of 5? It's 5 to the negative 2, isn't it? So I could just write down negative 2 here. But I want to show you again that if we just write this 1/25 is 5 to the negative 2, then I can use a property to get my final answer. What's log base 5 of 5 to the negative 2? So what property was this that we had? It was log base b of b to the x. It was the third property, wasn't it? It was the third property that says if you have log base b of b to the x, the answer is x. So this should just spit out -2. That would be your answer. That's the expanded form of that expression. Now, let's move to the next property. Property 6. There are 8 properties, okay? Property 6. Log base b of m divided by n. So the property I gave you just before was m times n, wasn't it? Multiplied? This is division. What do you think the division becomes? Subtraction, exactly. 2 logs again. It splits into 2 logs, but you have subtraction instead of addition. Now with subtraction, the order matters. Like, right, if I write 5 minus 3, that is not the same as 3 minus 5. When we do subtraction, you can't switch the order. Addition, it didn't matter. But with subtraction, it does. So the first logarithm gets the numerator. The second logarithm gets the denominator. All right, let's do an example here. If we do log base b of x, y, no, log base, let's not do b, let's do log base 10 of xy over 100. What do you see first here? What property do you see? You see 5. Where do you see 5? X times y. I do agree. I do see 5, but I also see 4. You see 4 because of what? 10, and then the 100 could be rewritten maybe? Okay, so that's in there. I agree. It's in there. And then property 6, right? We have division, don't we? xy over 100. So watch the way I write this. Tell me if you agree. Log base 10 of xy minus log base 10 of 100. Do you agree that I just used property 6 to split this up into 2 logs? And you all agree with that format? Okay. Now, how can you rewrite this? So you're going to use property 5 and split this up into 2 logs, right? So you have your multiplication here. So notice I did the division before I did the multiplication. All right, so now this splits into 2 logs. Log base 10 of x plus log base 10 of y. That's this split. And then I still have this log base 10. And how could I rewrite 100? Ten squared, right? 10 squared. And what's this log? 2. Now you could have got 2 from right here because you're saying 10 to what power is 100? Right? 10 to what power is 100? That's 10 squared, that's 2. But I rewrote 100 as 10 squared so you could see the property, the third property, log base b of b to the x equals x. Now we still have these logs out front. Log base 10. Can I do anything to these? No. Okay. 2 more properties. Property 7. Property 7 is probably the most powerful property of all of them. Let me make sure I use the notation they use. Why do they do that? Okay. That's your seventh property. I know that it looks weird because there's a lot of different letters in there. But what this property says is that if you have a logarithm, a base b, and you have something to a power. Now notice that this base does not match this anymore, right? So like this is not b and then b again. This is some other base and then raised to some power p. What is this property saying happens? What happens to that p? It comes out front and multiplies. So that p can drop in front. This is extremely useful. Here's an example. What is log base 5 of x squared? How can I rewrite that using that property? This is equal to 2 log base 5 of x. Right? That's what that's equal to. How about this one? How about log base 6 of the square root of x times y? xy log? What do you mean?
Oh, wait, you have to get rid of the square root.
We have to get rid of the square root. We cannot split this into two logs yet. We have to get rid of the square root first. So do you all know what it means when you take the square root of something? What power that's equivalent to? Raising it to what power? The square root is the same as raising something to the... No, that's squaring. No. It's 1/2. Hold on, I'm going to put it up here. If you have the nth root of x, that's equivalent to x to the 1 over n. So for example, if you have the cube root of x, this is x to the 1/3. If you have the fourth root of x, this is x to the 1/4. If you have the square root of x, we don't write it, but what number's out here? A 2. So this is why it's x to the 1/2. Right, these are properties of exponents, and these are called rational exponents, radicals, radical expressions, and rational exponents. This is how they're related to one another. So when I see this right here, I can actually take that whole x times y and raise it to the 1/2. That's the same as taking the square root. Then I can pop the 1/2 out using this property. Now what do you see? Do you see anything else you can do here? You can do the multiplication. This right here allows me to take this single log and split it into 2, right? That's property 5. So I can go 1/2. What do you think that 1/2 is going to have to do, though? Distribute to both. It's going to have to go to the first one and to the second one, like that. And that's all we can do. There's nothing more. Okay, we've got about 6 minutes. I think this will be a good time to stop. Look, your homework for tonight is to go off the schedule, the homework that's on the schedule. It should be just numbers 1 through... Let me just double check this here. I want you to try and do page 115, 1 through 33 odd. And yes, you'll probably run into some that you have some trouble with. You should not need a calculator for any of this at all. And I was rather disappointed on the test when I was grading them, and I would see obvious obvious work that, well, I didn't see any work. All I would see is like a graph. So it was like, graph the quadratic function and no steps, just a perfect graph at the end. Or, graph the polynomial function, no steps, just perfect graph at the end. And those students didn't get credit for that because all you're doing is punching in your calculator and you're not following any processes at all. So do not become dependent on your calculator. All this homework should be done without it, but bring your calculator next class because we will need it, all right? If you want your test, here they are. There's no grades on these. The grades are online. But all you have to do is add up the points that I took off and subtract it from 100, and that's your grade. I'll put them over here. One of these, it says, who are you? Because I couldn't read your name. I figured out who you were, so don't worry about that. You ready to roll?